Hey team, you ready for video number 6 in our chemical reactions journey? We're gonna bring it up a notch here. We've been just doing basic stoichiometry, maybe some limiting reactant stuff. But now we're gonna look at some situations you might run into in lab or in the real world, sometimes unexpectedly so. We're gonna look at several things: consecutive reactions, and how to deal with these. And in possibly this video, unless it runs too long, we'll go to another one on simultaneous equations, right? Multiple things going on at the same time you may not have expected. But consecutive equations is a pretty straightforward process, right? So let's say I have two reactants A and B, react them together and form a product C. Normally we're done with that. But in the real world, what if I take that product C and in a new reaction, react it and it goes bye-bye? So what you form in reaction 1 becomes a reactant and disappears in reaction 2. So it's the species, sometimes fleetingly so, we call an intermediate species. And these two equations are called consecutive equations. Reaction 1 occurs, and then reaction 2 occurs. And reaction 2 can't happen until reaction 1 starts, because the product in reaction 1 is the reactant in reactant 2. So you can't start 2 until 1 is done. Or maybe they're going on in sequence, right? Boom, boom, boom. And we can continue on and on and on. Maybe in reaction 2, I take the product and make a reaction 3, and take that product and do reaction 4. I did a high-level analytical chemistry class once, and I had 9 equations in a row. Oh man, did they hate me that day. But once you see how it's done, we can connect these through the intermediate species quite simply so, right? Once you get to moles of a species, you can convert it to moles of any other species in that balanced chemical equation. But if I have consecutive equations connected by a similar species, right? I've got the same species in equation 1 as I do equation 2, that intermediate species. I can now go moles of that species to another equation, right? Kind of like a double stoichiometry. And we're going to track that stoichiometry along through that species these equations have in common. So let's do an example, kind of show you how it works out. Really nothing new per se. It just adds one extra step in our stoichiometry calculations. We'll have two side-by-side mole-to-mole ratios from the two different balanced equations connected by the species. So let me throw something up. No, let me put something up on the board there, and let's have some fun with it. Here's something you might run into. Sometimes you run into things in lab, you don't even know you're running into them. Oh, you can get these side reactions that can cause error, especially if you're combusting something. When you're combusting something, you're reacting it with oxygen gas, right? But we're not going to let you use pure oxygen gas at the undergraduate level, right? Usually we'll just use air, and we'll take that, and it's about, 21% oxygen. That's usually good enough, like with a Bunsen burner. But the problem is, air is about 78% nitrogen, so you might, at elevated temperatures, not just react, maybe you're reacting a metal with, you're combusting a metal. Well, that metal can react with the oxygen gas, but if it's high enough temperature, it might react with the nitrogen gas in air too, and you get two products instead. You get the oxide and the nitride. Not bueno if that's not what you're after. So this is something you might run into. Maybe you're heating up some magnesium and trying to combust it, and a side reaction, it reacts with the nitrogen gas to form the metal nitride, in this case magnesium nitride. Not good. Let's say we want to get rid of that. So, and that's a kind of a greenish solid, so you'll be looking, oh, what's that? Where'd that green come from? I thought the oxide was white or something. So what we'll do is we'll take that nitride and just add some water to it, right? Heat it up, convert that to the hydroxide, plus you get ammonia gas, and you can actually smell a little bit. Oh yeah, that smells like ammonia. And we can continue on, heat that up and form magnesium oxide, etc., etc. But let's just take these two equations. Now notice these are consecutive equations. We're producing magnesium nitride in equation 1, and then taking that same magnesium nitride as a reactant in equation 2 and making it go bye-bye. So that magnesium nitride is called an intermediate species. It comes in equation 1 and goes in equation 2. So we can connect these two equations using magnesium nitride. Here's an example problem. What mass of magnesium, so we're solving for the magnesium, that's what we're after, must have reacted to produce 2.49 grams of ammonia. So we're starting here and working to get to the magnesium. So we're kind of doing it backwards stoichiometry. A lot of times we go reactants to products. Let's go products to reactants this time. But notice if I want to go ammonia, I got to get to moles, correct? So to get moles, once I'm in moles of ammonia from the provided information, I can't go directly to magnesium, can I? It's in a different equation. There's no, you can't use that mole ratio. You need to get from here to the species these two equations have in common, which is the magnesium nitride. So I got to go from the ammonia to the magnesium nitride. See that 2-to-1 mole ratio? And then once I'm in moles of magnesium nitride, now I can jump up to equation 1 and go 1 mole of magnesium nitride is produced from 3 moles of magnesium. Oh, double stoichiometry. I want you to set up a game plan for me. I'm not going to have room to do the problem, but we can set up a game plan. I want you to pause this and set up, starting with the grams of ammonia, each step in your unit line equation until you get to, and it just says mass of magnesium, so just leave it as grams. If you want to go to milligrams or pounds, have at it. But go ahead and pause it and set up a game plan and see if you get what I get. Ready? So let's take our grams of ammonia. Hopefully you know what ammonia is by now and what it smells like. If you haven't, take a little whiff. Make sure you do it properly. Do it properly. So let's take our grams of ammonia, and we should be able to use the molar mass to get to moles of ammonia. Right? Pretty standard. At this point, that's pretty standard operating procedure. We'll advance that later on down the road. In each chapter, all we're doing is just adding a new chapter and putting some new arrows in your quiver, right? That's all we're doing. But pretty much the foundation stays the same from chapter to chapter. Now I'm in moles of ammonia. I can go to any other species in equation 2. Let's go to the one that connects the equations. Let's go from ammonia to magnesium nitride. So I'm going to go to moles of magnesium nitride. Now that I'm in moles of magnesium nitride, I can go boop up to this one and go from moles of magnesium nitride to moles of magnesium. So we're going to have two side-by-side stoichiometry ratios, the stoichiometric factors. And once I'm in moles of magnesium, I can go to grams quite readily. And we'll just leave it as grams at that point. So this is a 1, 2, 3, 4-step problem. I'm going to erase the board, pop this baby out, have at it. Actually, I'll leave the equations up. I'll just erase this part, and then we'll move along this process. So start with 2.49 grams of ammonia. See if you get what I got. Have at it. I set up just the first step. All right, so I took my 2.49 grams of ammonia, used the molar mass to go to moles of ammonia, and again, you just add them all together. So we got 3 hydrogens and 1 nitrogen. So grab your hydrogen. Whoa, a little close there. 1.00794. We're going to times that by 3, and then add the nitrogen. 14.0067. Looks like 4 decimal places and 4 decimal places. So they both have 4 decimal places. That's why I have 4 decimal places in my molar mass there. But we're limited by the sig figs in the mass anyway. Now that we're in moles of ammonia, I can go wee, and let's do that 2-to-1 mole ratio. Right, let's set that up. Oh, where'd my pen go? So I have 2 moles of ammonia. That's an ugly looking ammonia right there. See that 2? And that's going to go to 1 mole of magnesium nitride. Stoichiometry step. Boom, boom, check. And once I'm there, now I can go from magnesium nitride here to magnesium there. So for every 1 mole of magnesium nitride, that's produced by burning up 3 moles of magnesium. See the double stoichiometry? We haven't done that before. Nothing new, we just haven't done 2 in a row like that. And you can just keep on going if you had a whole bunch of equations. And now we can just go to grams. Let's look up the molar atomic mass of magnesium. Depending on the periodic table you have, this one says 24.305. 24.305. So I'm going to squish that in there. So 24.305 grams per mole. Whoa, I need a longer board. And you can see all the units cancel out, right? So grams of ammonia, moles of ammonia, moles of magnesium nitride, moles of magnesium leaves you with grams of magnesium up there. So I got 3 significant figures here. 1, 2, 3, 4, 5, 6 significant figures there. This is exact, 5 there, so I'm limited to the 3 significant digits. So pop out your calculator, and if you set it up this way, you'll maximize your partial credit. If you make a boo-boo, maybe you have the fat finger syndrome on the calculator. I do all the time. I set it up, and I'm like, bleh. It's like I can't text where the darn. I'm like, oh, man, I spend more time correcting the mistakes than I do actually texting. So I'm like, oh. So I did that so many times where I'd set everything up perfectly and just hit the numbers wrong on my calculator. Like, oh. But if you have a professor that, depending on their philosophy, my philosophy is you set it up, it's nice and clear, but you accidentally did 24.035 or whatever. Yeah, your patient died in the real world. The bridge collapsed and you killed 1,000 people. Don't make those mistakes in the real world, right? But in college, I'll be like, okay, you set everything up right. Maybe I'll give you, the 13 out of 15 or something, right? Here we go. What did I get? So I got 5.3303 grams of magnesium. Good to 3 sig figs. So that's closer to 5.33 than to 5.34. So let's leave it as 5.33 grams of magnesium. So this is so 2 things in here. We worked it backwards, starting with the product, going to reactant. You can go any direction in stoichiometry, and a double stoichiometry. Let me show you another way we can attack this, where what we'll do is we'll combine the equations. Let's combine these, and anything that's the same on both sides, the intermediate species, cancels out. Ooh, it's kind of like algebra, but instead of x and y, we're using chemical formulas. Right? So Mg solid might be x, and Mg3N2 might be y, and 2y on one side and 1y on the other. You can subtract a y from both sides. It's algebra with crazy stuff. So let's pop that up on the board. All right, the second approach to consecutive equations, I think the first way we did is the easiest. You don't have to play any tricks. You just do the double stoichiometry. Piece of cake. But one thing we're going to do later when we get to thermochemistry and thermodynamics is we're going to combine equations together to get an overall simplified equation so we don't have to do the multiple steps. And there's purposes for that mathematically. So consecutive equations, the other option is let's add those together. And then everything on the left-hand side of the arrow for both equations goes on the left of the new overall equation, and everything on the right side of the arrow of both equations goes on the right. But what's interesting, you'll get the same. Sometimes you'll get the same species on both sides of the resulting equation. The intermediate species should cancel out, so that disappears, right? Comes and goes. But other species you might find like 5 waters on the left-hand side and 2 waters on the right-hand side. So you could subtract 2 waters from both sides and simplify that. So what we'll do is we'll add 2 consecutive or 3 equations together. Doesn't matter how many equations you got, just add them together. You'll get an overall equation, and then we're going to simplify that by reducing it, right? Sometimes you'll see a couple hydroniums on each side, which can reduce, or hydroxides or something. We'll do this a lot for redox reactions later on in aqueous solution. It gets pretty crazy. Let me throw an example up on the board. I don't think we'll do mathematics with it. I'll just show you generically how it works out, and you can see the overall equation, and you can just apply a simple stoichiometry problem to that. But let's pop one up on the board to see what I'm talking about. Similar to what we did last time, let's just do a different set. I could have used that same example problem as before and just combine the 2 equations and the magnesium nitrites. You could try it, right? Take the prior example, add the 2 together, and you see the magnesium nitrites cancel out. Woo, 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 woo. And you could redo that same problem with 1 stoichiometry step instead of 2, right? You combine the equations in step 1 and then do the stoichiometry with just 1 mole-to-mole ratio in step 2. But what we did is we just didn't combine the equations and just did them sequentially. But here we can combine them. For example, let's take some carbon dioxide if you're into environmental chemistry, anything like that. Carbon dioxide, obviously combustion of fossil fuels, et cetera, et cetera. One of the, if you're into this stuff, it's fun to research into it. If you're interested in it, if it's a passion for you. A lot of people are worried about that carbon dioxide dissolving in the oceans, right? What happens when that CO2 gets in the oceans? So people worry about the acidification of the oceans. Research it on your own, right? Don't take anybody's word at face value. That's what a true scientist will do. You go research it and find out. But that can produce the hydronium ion and the bicarbonate or hydrogen carbonate ion. That's scientific fact, right? So the acidification of that surface layer of the ocean. What are the ramifications of that? Well, let's take that acid and that can react with calcium carbonate. Now, not my specialty, but I think shells and things like that, I think, are made of calcium carbonate. Again, not my forte. But one of the worries about that is the thinning of those shells, and how will that impact marine life that depend on those calcium carbonate shells. All right? I don't know. That's an extension. That's where it goes from the chemistry to like the marine biologist or something. I was just the chemist, okay? But I know that reaction happens. Hydronium ion can react with that to extract the calcium ion out with the bicarbonate ion and water, making the solid shell go bye-bye or thin out. We could do a double stoichiometry problem with this, right? You see how they're connected by the intermediate. So I could go like moles of this to moles of that, and then moles of that to moles of this, just like we did last time. But what we're going to do this time, we're going to add these equations together. Let's do it. Let's add these together. You don't have to put the thing there, but I'm obviously adding this together. Let's take everything on the left-hand sides of the arrows. The carbon dioxide, the water, the hydronium ion, and the calcium carbonate. They're all on the left-hand side. Let's put them all in one equation. And then everything on the right-hand side, the hydronium ion, bicarbonate ion, calcium ion, another bicarbonate ion, and the water, put those all on the right-hand side. And you're going to get this overall equation. Go ahead and do that for me real quick. Don't simplify yet. Just get the overall equation. So pause it and do it. I'll write this out. These are pretty long, so they're long and bulky, so we're going to simplify them. We're going to do this a lot in chemistry, a lot in thermodynamics, a lot in redox and solution. So let's take the CO2 gas. I see that on the left. I see the two waters. And that's everything for equation 1 on the left-hand side of the arrow. Now let's go to equation 2 on the left side of the arrow. I see the hydronium. And I see the calcium carbonate solid. And let's draw an arrow. Boop. Obviously, I can't fit this all in one line, so I'm just bringing this down. Now let's go to the other side. See the hydronium and the bicarbonate. So that's everything on the right-hand side from equation 1. Equation 2, I've got the calcium ion. I've got another bicarbonate. And I don't know, in the old days we learned it as bicarbonate ion. Now most people call it hydrogen carbonate. And then we've got a water here. That's what we call the overall equation. Very bulky. Let's clean this up, all right? Let's take this. Do you see the intermediate species, the hydronium? Do you see that right here? So I've got one hydronium on the right-hand side and one hydronium on the left-hand side. Would you agree? Those cancel out. Isn't that slick? So what we're going to do is we're going to simplify this. And just clean up the extraneous details. So the hydronium, the intermediate species, goes bye-bye. Do you see anything else that's the same on both sides? Do you see a carbon dioxide gas on the other side? No. Do you see water on the other side? Oh, I do. Look at that. I have one water here and two waters there. So kind of like a 2x on one side and an x on the other. Let's subtract x from both sides. Let's subtract a water from both sides. So that water goes away, and that goes to 1, right? So 1 minus 1 gives you no waters left on the right-hand side. 2 minus 1 gives you 1 water left on the left-hand side. These two bicarbonates are going to combine together, right? So I'm just going to lump those together as two bicarbonates, and then the calcium. I don't see calcium carbonate on either side. So that's it. I don't see anything else canceling out. Let's do our overall equation. So I still have the CO2 gas on the left. I have one water left. The hydronium's gone. Hydronium ion's gone. I have the calcium carbonate solid. And that's it on the left-hand side. Got rid of the hydronium, got rid of one of the waters. Yay! On the right-hand side, the hydronium ion, the intermediate species, is gone. I got two bicarbonates. Do you see that? 1, 2. So I'm just going to combine those together to go to 2 bicarbonate ions. Boop, lump them together. I still have the calcium ion here. And that water's gone. So all we're left with is the simplified overall. We call that an overall equation, just the sum of two or more equations, getting rid of the intermediate species. We'll do some more advanced tricks later on down the road in thermo. So we can kind of look at that, and you'll see this a lot in papers and things. People will just give you an overall equation. This is what happens when the CO2 gas goes in water and dissolves the calcium carbonate shells, producing bicarbonate and calcium. But really, it happens in two sequential steps. We'll do this a lot in kinetics when we do reaction mechanisms in second semester general chemistry. We'll have this overall equation go, well, really, that's due to these three molecular steps. 1, 2, and 3, and when you add them all together, this is your net result. It's going to happen all the time. So this is your brief little introduction into them. And now I could apply a problem to this, right? I could say, hey, how much calcium carbonate was dissolved to produce, this many milligrams of calcium ion or whatever. And you can now do this as a one stoichiometry, 1 mole to mole ratio step, or you could just treat it as two sequential ones like we did before. So 2 ways to skin a cat on sequential equations. So this went a little long, so let's do simultaneous equations, which is a little longer as far as the problems. We'll do that in a new video. You guys are awesome.